Good morning. Today we're going to be talking about an overview of uniform circular motion, which is related to rotation, which we have been focusing on for the past week or two. So just to start out with a quick concept review and build upon that, we're going to start out with a few general equations about rotation, most of which we've already used within class examples and homework. Okay, so again, we have two different types of motion that we focus on, translational and rotational motion. Today we're going to add in a third component. So we have motion tangent to the circular path. We have motion that is measured in relationship to the center of a circle. And now we're going to be talking about centripetal components, meaning components of accelerations and forces that point towards the center of an object's motion, and really work to explain why and how objects rotate in a circular path. Okay, so to start out, let's just review some of our rotational variables here. Rotational motion is the rotation of a rigid body about some fixed axis, which is usually its center of mass. Rotational motion can be described using the same kinematic values as translational or linear motion. We're looking for position or change in position. In terms of translational motion, we take that straight line distance from where we start to where we end, and that gives us delta x. When we're talking about angular position, however, we need to identify, in respect to the positive x-axis, or some reference line, which is assigned for us, we need to determine the initial angular position, theta, measured in radians, which is a distance r from the center of the circle. We can describe the linear length between that reference line and our secondary position here using a variable called arc length. So arc length is the length of the arc. It's a linear distance that the object travels around the circular path. And we use a lowercase s to represent that variable. Our angular position is related to that variable as the arc length, s, divided by the radius of the circle, r, will give us the angular position, theta, measured in radians. Okay, so our angular position is the arc length divided by the radius. You can also find arc length if you rearrange this a little bit. Arc length is equal to the radius times the change in angular position, where again, delta theta should be measured in radians. In terms of displacement, again, we take the final position and we subtract the initial position to find delta x is equal to final minus initial. In terms of angular position, we're taking the initial angular position, or delta theta, and we are subtracting that from the final angular position, which is measured in respect to, again, the positive x-axis. So to find the change in position, our change in angular position, we take the final angular position in respect to the origin or reference line, and we subtract our initial angular position, where again, delta theta should be measured in radians. Velocity and acceleration have reciprocal relationships to those from the linear motion units that we've talked about. Angular velocity is the rate of rotation, so it's going to be the change in angular position over time, which should be measured in radians per second as well. In terms of acceleration, we take our rotational form of velocity, which is omega. We determine the change in angular velocity over time, and that gives us our angular acceleration, in which angular acceleration is measured in radians per second squared. Okay. Quick conversion, right? We know that delta theta needs to be measured in radians. If you have degrees or revolutions, you can easily convert from revolution to radians or degrees to radians. Okay, 2 pi radians is equal to 360 degrees, which is equivalent to the term 1 revolution. So when you see 1 revolution in a problem, what that means is that the object has traveled 360 degrees or 2 pi. Okay, so an angular acceleration alpha is a constant value. We can use constant acceleration kinematics to find missing information, such as the initial angular velocity, the final angular velocity, or the change in angular position. We call this UCM for uniformly angular motion. On the AP exam formula sheet, you're given these 3 equations. They're written slightly differently. You're also given those same 3 equations in terms of the angular variables on the bottom left-hand side of the equation sheet. Okay, so if A is constant or alpha is constant, we use the big 4 equations in terms of our rotational variables. Okay, so alpha being constant is a special case. We also know that alpha could obviously equal 0, or the object can be accelerating, which means alpha is greater than 0. Okay, to determine alpha when it's greater than 0, we need to use the rotational equivalent of Newton's second law. Okay, when an object has angular acceleration, that is caused by torque. Right, torque causes angular acceleration. Torque is the rotational equivalent of force. It causes objects to rotate when that force is applied at a radius from the axis of rotation. Our equation is actually a cross product. It's R cross F. Cross product of 2 vectors gives us a vector. So torque is itself a vector quantity. If the radius and the force are not perpendicular to one another, we have to use the polar coordinate version of torque, which allows us to take a look at the angle between our radius and our force. You take the sine of the angle between those 2 vectors and multiply by the magnitude of those vectors to find the torque, or the rotational equivalent of the force acting on the object to cause that angular acceleration. The units we use are Newton meters. As we stated before, if the radius and the force are perpendicular to one another, the sine of 90 will give us 1. Okay, so if the forces are in fact perpendicular, we do not need to include that polar notation version of the equation, which considers the angle between the two vectors. In terms of direction, right, we say that counterclockwise, CCW, rotation is considered positive, and clockwise rotation is considered to be negative. So torques that are negative cause clockwise rotation, torques that are positive cause counterclockwise rotations. In the case where angular acceleration is equal to 0, meaning that there is no change in angular velocity over time, we consider the object to be in both rotational and translational equilibrium. So the net torque acting on the object is equal to 0, but the net force acting on the object is also equal to 0. So there is no angular acceleration. When angular acceleration is 0, we have two options. Omega, our angular velocity, is either also equal to 0, meaning the object is not rotating, or omega is a constant value. If omega is constant, that is a special case within circular motion, and we call that uniform circular motion, which we abbreviate as UCM, uniform circular motion. Which we're going to head into right now. So uniform circular motion is when a particle moves around a circular path at a constant speed. That circular path has a constant radius of length r. In uniform circular motion, one defining characteristic is that the velocity is tangent to the circular path. So what that means, tangent, as we draw tangent lines on our curvatures to determine, let's say if this is a, yikes, what happened there? There we go. Let's say this is a position versus time graph. To find the velocity, we would draw a tangent line, a line that shares the curvature at that respective time, but is tangent to that path of motion. Same thing follows through with our velocity. So the object's velocity, that velocity vector shares that path of motion at that instant, but the velocity vector itself is tangent to the circular path. Regardless of the location of the object around that circular path, that tangential velocity is constant. It remains the same. So the magnitude is constant. As you can see here, while the length of the vector remains constant, the direction in which that vector points varies. Okay, so the direction is not constant. Only the magnitude of the velocity is constant. So direction is constantly changing. So the direction of that constant velocity is going to change, but the physical magnitude of that velocity remains the same. Typically in nature, we see this when we have an object such as a stopper or a ball at the end of a string, and we rotate that string around our head. If you were to paint a dot on your bicycle wheel and spin that wheel at a constant or consistent rate. In nature, we see this when we have satellites orbiting Earth, or even Earth orbiting the sun. We assume, or we can basically model that motion as uniform circular motion, which means that this velocity here is constant. We discuss tangential speed, which we're going to use the variable v sub t to represent, in relation to the period of rotation. So just like the period in a school day, right? Whether it's English, math, science, one period is a consistent length, 78 minutes. We're talking about period in terms of rotation. Period is the amount of time it takes for that object to complete one revolution. So it takes 78 minutes to complete one period in our day. Period itself, which we use capital T as a variable to represent, is the time it takes the object to make one revolution, meaning it has traveled 360 degrees or 2 pi radians. Can we relate that time to the circumference, basically total ground that that object has covered? And we measure that time period in seconds. That tangential velocity, which we previously discussed, is a way in which we can measure the rate of travel of that circulating object. So our tangential velocity is our circumference, the circumference of the circle, divided by the time it takes to complete that entire path, one time, one revolution, which we call the period of rotation. So the equation for our tangential velocity, that constant velocity, in which objects with no angular acceleration typically contain, we can find that tangential velocity by multiplying 2 times pi, so the angular change of position, by the radius of the circle, and we divide by the period, the time it takes to make that full revolution. Okay, so let's try an example. Okay, so a 0.5, let's try a little bit harder example. Okay, so let's take a look at this example. We have a 4 centimeter crankshaft that turns 2,400 RPM. RPM is an abbreviation for revolutions per minute, just like mph is miles per hour, something that you'll just have to get used to seeing. What is the speed of a point on the surface of the crankshaft? Again, we're assuming that this is uniform circular motion. Okay, you can see an example of what a crankshaft is down here on the right-hand corner of the screen. So basically, we're looking at a point on this rotating crankshaft that's located at a radius r from the center of that circle. We're actually given the rate of rotation, right? We're told it makes 2,400 revolutions every minute. That is our rate of rotation. So what that's telling us is rate of rotation is omega, our angular velocity. So we're given our angular velocity, 2,400 revolutions per minute. We're given the diameter of our crankshaft, which we need to convert to determine the radius. Radius is going to be half the diameter, so we get 2 centimeters. And we're looking for the tangential velocity, or that constant speed. We know that tangential velocity is 2 pi times the radius divided by the period. And from our previous classes, we also know that velocity or a tangential velocity, and our angular velocity are related by the radius r. So tangential velocity is the radius times the rate of rotation, or angular velocity. It's also 2 pi r times our period. In this case, we're not given the period, we are given angular velocity. So we want to use our original equation we've discussed to find that tangential velocity. We could go back from there to find period if you wanted to. Okay, but let's start with our tangential velocity equation. Okay, so basically here we're going to first convert so that omega is in the right units. Omega should be measured in radians per second. So angular position is radians. So that means that angular velocity must be radians per second, as the equation is delta theta over time. When we convert, we're going to multiply by 2 pi to get rid of the revolutions. Divide by 60 seconds to convert to seconds. We get 251 radians per second. Once we have the angular velocity in the correct units, we can plug into our relationship for tangential velocity in terms of rotational velocity. So we get 251 radians per second times 0.02 meters. We got 5.02 meters per second. Okay, one more quick example. We have a 0.5 kilogram mass attached to a 1 meter string. So that tells us that the radius of our string is 1.5 meters. We're given the mass of the object, and that object is whirled in a horizontal circle. Each revolution is completed in 0.5 seconds. So that tells us that the rate of rotation is constant. So from that information, we can actually approach this in one of two ways. Right, omega is our rate of rotation. It's a change in position over the change in time. So we could say, right, that our angular velocity is 1 revolution per 0.5 seconds, and use that radius, r, to find tangential velocity in the same way we did in the previous question. To shake it up, we'll use the other equation for tangential velocity, just so that we can see both applications. Okay, so we're going to use the version of tangential velocity in terms of the circumference and period. Period is the time it takes the object to make 1 revolution. According to this example, 1 revolution occurs every 0.5 seconds. So that value gives us our period t. And we also given our radius. So to find the tangential velocity, we can take 2 pi times the radius of that circular path, which is 1.5 meters, and divide by 0.5 seconds. And we get 18.85. Our units, technically 2 pi, the implicit unit is radians. Radian times meters, we get meters over seconds. So tangential velocity is 18.85 meters per second. Okay, so let's transition into why objects move in a circular path. Yikes. As we already discussed, our linear meaning translational quantities and our rotational quantities are directly related to each other. So an object is moving in a circle, it has tangential velocity. that tangential velocity, the magnitude of it is constant. We can relate the arc length, meaning the linear distance in which an object travels along a circular path, to its change in angular position using the arc length equation. So this linear distance here, s, is the product of the radius, r, in meters, multiplied by angular position in radians. Our linear or translational velocity, which we said was a constant magnitude, we can determine by taking delta theta and multiplying by the radius of the circle in meters, dividing by the time it takes to travel that delta theta. Specifically here, right, delta theta over delta t is the definition of omega. So that's where that equation for tangential velocity originates from. So delta theta over t is omega times r. So omega times r will give us the tangential velocity, which its magnitude is constant, but its direction changes. The reason why its direction changes is because we have a net centripetal or a net center-seeking force. So objects only move in a circle due to a net inward or center-seeking force. You'll see that referred to as either centripetal or radial. Unfortunately, they really interchange the two, so you have to be comfortable enough with both sets of terminology. So the reason in which our tangential velocity changes Is this recording? It's not really working very well. Just need to... Oh, it is being recorded. Okay. Alright guys, for the interruption. I wanted to make sure I was recording. I wasn't able to move from slide to slide, so I wanted to make sure I was recording. So tangential velocity is related to the change in the object's direction, which is due to a center-seeking acceleration, which comes from a net or center-seeking force. Okay, so this inward force causes a net acceleration. That acceleration, which we either call the radial velocity for a sub r, radial acceleration for a sub r, or radial or centripetal acceleration for a sub c. So that change in the object's tangential velocity is due to that constant center-seeking force. Right? The net force is always pointing towards the center of the circle, so our velocity is going to change direction in that same direction, in the center-seeking direction. So our radial or centripetal acceleration is responsible for the change in our tangential velocity's direction. In uniform circular motion, the tangential velocity is constant. The magnitude is constant. If the magnitude changes, that's due to an angular acceleration. If there is an angular acceleration, meaning that alpha is not equal to 0, the object also experiences a tangential acceleration, which is the product of the relation between the radius of the circular path and the change in angular velocity over time, which is the definition of alpha. So if the velocity of the object, the magnitude changes, we have tangential acceleration. If only the direction changes and the speed is constant, alpha is equal to 0. So that means that the tangential acceleration is equal to 0. And the only component of acceleration would be the radial or the centripetal acceleration, which we can determine by squaring the tangential velocity and dividing by the radius of the circle. Okay, so let's apply this to an example. So in this concept example here, we have an object that is rotating in a circle at a constant rate. So if the rate of rotation is constant, that means omega, our angular velocity, is constant. If our angular velocity is constant, our angular acceleration is equal to 0. If angular acceleration is equal to 0, that means that our tangential acceleration is equal to 0, as tangential acceleration is the radius of that circular path times the angular acceleration. So that's also going to be equal to 0. In order for an object to move in a circular path, it must have a center-seeking force, meaning a acceleration in that same direction. So we have centripetal acceleration. So in order for tangential velocity, the magnitude of it, to be constant, like our rate of rotation, centripetal acceleration cannot be equal to 0. Okay, so let's look at our answer choices. So our angular acceleration has to be 0. So that immediately knocks out A and B. Tangential acceleration also has to be 0, as alpha is 0. So that still leaves B and D. Last one, centripetal acceleration cannot be equal to 0. So that eliminates A and B. My answer choice is option C. Okay, as we stated before, the centripetal acceleration is caused by a net centripetal force. So let's talk about what a net centripetal force is. Okay. So an object moving in a circle at a constant speed experiences this acceleration, and that acceleration is directed towards the center of the circle. This centripetal or radial acceleration is due to a change in that direction of our tangential velocity and not the magnitude. You notice there that the length of the vector quantities are exactly the same. The only thing that changes is the direction. What is responsible for that change in direction is the net force in the centripetal or the radial direction, which causes an acceleration in the centripetal or radial direction. Again, as we stated before, we can find that center-seeking acceleration by squaring the tangential velocity and dividing by the radius of the circular path, r. This centripetal acceleration is caused by some centripetal net force. Centripetal forces are not drawn on a free body diagram. Centripetal force is a type of net force. So just like force in the x, force in the y, it's a type of net force. So it's a term we use to describe any force that causes an object to move in a circle, but that specific force is specific to the situation. Could be tension, could be force of gravity, could be friction. But centripetal force itself is not a force. It's a category of forces that describe forces in which allow objects to move in a circular path. To derive our equation, we're going to use Newton's second law. So any net force is equal to the mass of the object times acceleration. So if we specify or substitute out F net with F centripetal, and we plug in for A centripetal, we find that the net force causing the object to move in a circle is equal to its mass times its tangential velocity squared divided by its radius. That centripetal force is going to follow along the same pathway as the centripetal acceleration, right? Net forces cause acceleration in the same direction. Okay, as we said, centripetal force is a type of net force. It's going to be due to the force of gravity acting on an object, the tension in a string, the normal force of a track on a roller coaster, or the force of friction. It is not drawn on a free body diagram and is not a force itself. It's a category of forces based on the force that causes the object to move in a circular path within a given scenario. Okay, so let's take these equations and apply them to a few separate examples. Okay, so let's say that a ball rolls over a ball of mass m rolls over the top of a hill of radius r with a speed of v. At the top of the hill, what is the magnitude of the normal force exerted on the ball by the road? Okay, so our first step here, we want to draw a free body diagram for our ball. So we know based on the road's going to apply a normal force of the surface on the object at a 90-degree angle or perpendicular to that road. We also know that the downward pull of gravity, m times g, is acting on the object as well. We want the magnitude of the normal force exerted on the ball by the road. Okay, so what's interesting about this, instead of summing the forces in the x and the y, we want to find the radial or the centripetal forces. So any force that points away or towards the center of the circle. Notice here that normal force points away from the center of the circle. So it's going to be in the negative direction. So our normal force is opposing the net force or the acceleration of that system. So it is negative. It is not center seeking. It does not point towards the center. It points away from the center. So it's negative. Any force that points towards the center or is center seeking for circular motion, we label it as positive. So let's plug it in and solve. So I'm going to have negative normal force plus mass times gravity times mass times the acceleration due to gravity. Times mass times the centripetal acceleration, which we know is tangential velocity squared over the radius. If we just solve for f of n ourselves, we're going to add it to both sides of the equation and subtract over mv squared over r. So our normal force is equal to mv squared over r. Excuse me, I'm sorry. Getting a little tired here. Here we go. F of n is going to equal m times g minus m times v squared over r. We're trying to go with answer choice B here, closest answer choice. Okay, next up,